It's a pleasure to have Mark Rudelson, who will tell us about lower estimates of marginal density.
Thank you. And I'd like to thank the organizers for inviting me. I hope to be in Berkeley physically, but this is not possible. And I realize that this is the last talk of the workshop. This is Friday evening. So I'll try to make it shorter, but we'll see. This is a joint work with Hermann Koenig from the University of Kiel. And this is about the question which was asked some time ago by statisticians. And this morning Boaz said that there are three main topics of this workshop: log concavity, concentration, and hypercube. I'll try to check as many boxes as possible. There will be a lot of log concavity. There will be some ideas from measure concentration. There will be no hypercube, but there will be a substitute, a discrete solid cube. So let's start. And I'll start with a known theorem that if you have a vector with IAD coordinates having bounded density, regardless of the moments, and you take a marginal of this random vector, you project it on a subspace of dimension d, then the maximal density of the marginal will be bounded in terms of the maximal density of the original random coordinate and the factor depending on d. And there was a question whether one can derive a similar lower estimate for the density. So the question, let's make it more concrete. The question I was asked was, suppose that we have a density which is bounded below on a symmetric interval. Is it true that we can bound the density of the marginal if we evaluate it at the point whose norm is less than the same a? With the factor independent of the ambient dimension n. Why this can be plausible, let's take one example. Let's take the normal random variable. Then the marginal is also normal, and this estimate is obviously true. Unfortunately, it's pretty easy to come up with a counterexample. Even if you assume the expectation is 0, the variance is 1, and fast decay even boundedness. You just take the density 1 on the small interval and add to delta functions. Of course, delta function doesn't have a density, but this is an artificial obstacle, you smoothen it. And then even the density at 0 will be dependent on the ambient dimension, even if you consider a hyperplane. So if we cannot do this for any density with light tails, maybe we can do it for some more general density than just the normal one. And then the question was whether you can do it for the uniform density. And I consider uniform density of negative 1/2 on negative 1/2, 1/2, just to have the density 1 and not to carry it through the whole talk. It took some time to figure out what's going on with this question, and after it was figured out, unfortunately, the statistician didn't come back to me, so I lost the original source of this question, but the question turned out to be quite interesting on its own. And if we consider uniform density on -1, 1, we can reformulate it geometrically. The product density is the uniform density of the cube of the unit volume, and then the marginal density is just the volume of the section. So we can reformulate it saying that whether it's true that the volume of any section of the cube at the distance at most 1/2 from the origin can be bounded below. And since this is about sections of the cube, there is a large body of research on the question. Fortunately for us, first, everything is known about the central sections, not only the precise estimates, but the precise position of the minimal and maximal section. So for the minimal section, the position is a coordinate subspace. And of course, in this case, the section is a cube, so the volume is at least 1. The maximal section was explicitly described by Ball, and the volume is at most 2 to the d/2, and this is exact, and the maximal section is not a diagonal. Much less is known for non-central.
It's not always exact.
Sorry?
It's not exact for it's exact for d bigger than
Yes.
n/2.
Yes. Actually less than, not bigger, but less.
It depends on whether d is a dimension of E, right?
Yeah.
Okay, that's it. Okay.
Okay, much less is known for the non-central section, and actually the results appeared only a few years ago. First, the maximal hyperplane section was determined by Moody, Stone, Zak, and Zvavich a couple of years ago, but in the case where the shift has a large norm. The meaning of this large norm is that the section and the subspace is a hyperplane. The section by this hyperplane leaves only one vertex of the cube in one half space, and the rest of the cube is in the other half space, so it is easier to analyze. And very recently, Kaldowski and Koenig obtained an upper estimate for the hyperplane sections. And one take from this comparison of central and non-central results is that the position of the maximal section would depend on the distance. For the very large distance, it is diagonal. For the central one, it is not. So the problem, what was going on at the distance 1/2 may be more difficult, and actually it is, because it's extremely sensitive because of this 1/2. Let's see, if I take the vector in the coordinate direction with a norm less than 1/2, the section will be, of course, of volume 1. But if I take it with the shift of norm greater than 1/2, it misses the cube entirely, and the volume is 0. And if I keep it 1/2 but rotate it slightly, it is about 1/2. So it doesn't, even if you stay below 1/2, it is not continuous. Okay. So this is our question, and let me pass to the results. First, for the general dimension, we have this result. It is true that the volume of the section or the marginal is bounded by a quantity independent of the ambient dimension n. We haven't written this function phi, but if you trace the proof, the dependence is pretty bad. It's exponential in poly D. I'll discuss later the question whether one can do anything better, but at least it is a function of D only. So in a nutshell, the proof has two main ingredients. First, it's a kind of a soccer type. We repeatedly pass between the probabilistic and geometric version of the problem until it gets almost trivial. And so the second main ingredient is that we have different shifts and we are going to treat them differently. We will consider the vectors which are compressible and incompressible. The compressible vectors are vectors with a few large coordinates, and the norm is concentrated on these large coordinates. It's a vector close to the low dimensional subspace, and the incompressible vectors are the rest. This idea was introduced about 15 years ago in random matrix contexts, and then it became a standard tool there. Here, the question has nothing to do with random matrices. Nevertheless, this decomposition pops up. So before we treat even compressible vectors, let's treat the vectors which are very compressible, namely vectors with a very large coordinate. So our goal is obtaining the probability density, the lower bound for the probability density, and it is possible to obtain it. Let's consider the projection where we on the subspace, and this projection forms a decomposition of the identity. Consider a partial case where one of these vectors has a huge norm, the norm almost 1. So the subspace is, the kernel of the projection is almost orthogonal to the coordinate axis. Then, because we have such a nice expression, it's possible to use the characteristic function and especially manipulate these characteristic functions to reduce it to what Ball did. But we need another condition on the direction of the shift. We don't want to spoil this decomposition, and the shift is going to be parallel to one of the projections of the coordinate axis, namely to this large one. Then, just for algebraic reason, the calculations go through. So we got a discrete collection of the directions and shifts in which our inequality is established. Let's start from it and let's try to use some stability. And indeed, there is stability, and this is guaranteed by geometric property, namely by log concavity. So what we can do, we have to keep this condition that one of the projections is very large, actually even reducing this epsilon of d, but we can move the vector V slightly. It's not parallel to this direction, but almost parallel to it. We can move it a little in the orthogonal direction, and then our bound will still hold. The reason for it, I consider the density as a function of t. T is the shift in the orthogonal direction. And this density being a marginal, the log concave density is log concave. I know that if t is 0, it's large. And log concavity precludes to a fast decay of this density. So it will remain large in a small interval. Okay, so we got this estimate for a very small portion of this sphere. Let's extend it. And now I'm going to switch to compressible vectors. Before it, combining this, I can cover the part of the directions where the L infinity norm is almost 1. Remember, V is a unit vector. So the L2 norm is 1. So it's almost coordinate directions. Now let's switch to compressible vectors. What happens for them? First of all, compressible vectors carry non-negligible mass on small coordinates. So I take delta being a small number and consider the set of small coordinates. And these coordinates carry a non-negligible mass. Then I can drop all large coordinates and use the Berry-Essen inequality, and it would yield that this probability is large. The problem is that this is the probability of a half space. It has nothing to do with the density. And to connect it with the density, we again use geometry and again use log concavity. So let's consider the set, the upper level set of the marginal density. Since it's log concave, this is a convex and symmetric set. And then my point 1/2 V lies on its boundary. I take a supporting hyperplane and I draw a normal to this hyperplane inside the subspace E-proof. Here U is a unit vector and tau is the scaling. And just from the picture, we see that tau doesn't exceed 1/2. This is absolutely trivial. The norm of 1/2 V is 1/2. But this trivial observation will be helpful later. Okay, so this is the picture, and then it turns out that you can relate the density of the marginal at the point 1/2 V and the measure, the probability of the half space above this supporting hyperplane. This is also due to the log concavity of the marginal density. In process of it, unfortunately, we gain the power D, and this power is the major source of the loss of precision. Okay, so what did we gain? First of all, we reduced bounding density to bounding probability. Second, our subspace had a general codimension. Here we are in the situation of the codimension 1. This is just the inner product. And this is what we are going to bound below. As soon as I have this, I can combine it with Berry-Essen and be done with incompressible vectors. Great. So what remains is compressible vectors. Let's consider compressible vectors, and those are vectors for which the small coordinates carry only a small norm. And we can consider, as we saw before, we can consider only the inner product. So we decompose this inner product into the small and large coordinates. And when we applied Berry-Essen, we dropped the large coordinates and worked only with the small ones. Here I'm going to do the opposite thing. I drop the small coordinates and work with the large ones. Actually, we can drop any set of coordinates. Okay. And so we reduced our problem to the same one, but instead of the vector u, we consider the vector w, which contains only large coordinates. And for convenience, I normalized our inequality by the norm of w. So it looks very much like what we need. We did some translations and returned more or less to the original problem. What did we gain? The gain is in the dimension. The set of large coordinates cannot be too large. It has at most d to the negative 2 elements, delta to the negative 2 elements, and delta is dependent only on the dimension d and is independent of n. And now, since I am looking for the estimate which is dependent of d, I will define with the estimate which depends on the ambient dimension. By the way, this argument can be carried over without any compressible and incompressible part. We can drop all coordinates except a few and write the problem like this. So why did I tell the previous story? The reason is in this normalization. We remember that tau was less than 1/2. This was a triviality, but now I normalized it, and tau over the norm of this vector can be greater than 1/2. And if the shift is greater than 1/2, we can miss the cube entirely. This will be 0. So we have to make sure that this doesn't happen. Let's analyze when it happens. Okay, our vector is compressible, which means that the small coordinates carry only a very small mass, which means that the vector w has norm almost 1. Tau is less than 1/2, and tau divided by norm of w is greater than 1/2. When can it happen? First of all, it can be only slightly greater than 1/2. And if it is slightly greater than 1/2, and we miss the cube, it means that our vector is close to one of the coordinate directions. Its L infinity norm is large. And this allows us to finish the proof. So if the section doesn't miss the cube, obtaining a dimension-dependent estimate is not a big deal. This is basically elementary convex geometry. And if this norm is large, this case has been already taken care of at the very beginning. And then, summing up, we finish the proof. If we are not going after the precise bound. Any questions at this point?
So I was wondering, do you think that going after precise bound would be possible if you do a more precise decomposition? And what comes to mind is actually, I think your paper is Bosak, or just maybe in this case, you would need to like split compressible and compressible by the levels of delta, from delta being 1/n to delta being 2/n.
No, this is not about the finer decomposition. There is a weak point in this argument, and the weak point is here. As soon as you try to pass from density to probability, you incur a big loss. Okay. So now let's consider one partial case, one-dimensional marginals or hyperplane sections. And let's go after a reasonable bound, not just any bound. And here we can provide some numerical bound. This 1/17 is by no means precise, but this is not far off the optimal thing. Actually, it's only 5.2 times smaller than the possible optimal bound. And this 5.2 is obtained by comparison with the diagonal subspace, the hyperplane orthogonal to the diagonal vector. And the proof here has nothing to do with the previous one. There we worked with translations between probability and geometry. Here it's pure analysis. And we start with the formula for the volume of the hyperplane section. Hermann found it in a 1913 paper of Polya, but it's possible that someone found it even earlier. This is just using Fourier transform and Fourier inversion formula. And this is, of course, a highly oscillating integral. It didn't prevent Ball from obtaining his result, but this cosine messes the things up significantly. And we know it's highly unstable. If I put here a coefficient close to 1, it changes everything. So the first aim would be to write a different formula for it, which is stable, which avoids oscillating integrals. And this is possible. We can represent the volume as the integral of a positive quantity. So let's consider independent, identically distributed vectors on the two-dimensional sphere in R3. And then the shifted section will be the integral of the reciprocal of the norm of the linear combination of these vectors with coefficients which are coordinates of A, and the integral is taken over the set where this norm is at least 1. it doesn't look very much connected to the Polya's formula, but actually it is the same. And the proof is a very easy exercise in Fourier analysis. So the first observation, and this is one of the first exercises in a usual convex geometry course, that if you take a unit vector on S2, take its one-dimensional marginal, it's a uniform distribution on the interval, which allows us to rewrite this sinc function as a Fourier transform of the inner product of U against any unit vector. We can do it for each sinc function, and so we'll get that this product of sincs is the integral of these exponents. Then we sum up the product of the exponents is the exponent of the sum, and then we apply the same equalities the second time, translating this exponent into the sinc function. So now I have here a sinc function, but this is a one sinc function, not the product of sinc functions. And then we complete Polya's formula, integrate by parts, use Fubini and simple counter integration, and we are done. Well,
May I ask a stupid question?
Yeah.
But didn't Polya derive his formula from your lemma, and the lemma derived geometrically? Like, this would be the natural logic here.
I didn't read the paper of Polya, but I believe it was done the simpler way, using the Fourier inversion formula directly. It's
Sure, it's just that the lemma
1938
seems
paper
like the
in German.
geometric kind of basis for it, but maybe I'm completely wrong. So anyway, so sorry.
So almost, I said Fubini. Fubini is not cannot be applied here because we have s in the denominator. The function is not L1, but we still can justify switching the integrals, although this requires some work. Okay, so we have this formula, and sorry, we have down below this integral. First, let me rewrite it by just standard integration like this. And we have the integral of the probability that it's between 1 and something large. Let's look at this quantity. U is uniformly distributed on the sphere. It's a sub-Gaussian vector. The linear combination would be sub-Gaussian. Its norm decays quickly, and so the action occurs when this norm is relatively small. And when it is relatively small, we can bound it, essentially we can bound it below by the probability that this norm is at least 1. Okay, let's simplify it even more. If it is at least 1, I can square it for free, and then I can develop the square, cancel 1, which is the Euclidean norm of A, and I'm left with this quadratic form. I have to estimate the probability that this quadratic form is not negative. At this moment, we can forget about the original problem. We have a quadratic form of some vectors, and we want to estimate the probability that it is positive. So what do we know about this form? Trivially, since it lacks the diagonal, the expectation is 0, but this random variable is not symmetric. So we have a random variable with expectation 0, and we want to estimate the probability that it is positive. And nice exercise, and it should be known, but surprisingly, not very much is known about it. The only reference we know was given to us by Stashik Kvapin. It's the paper of Verar addressing exactly this problem, but the estimate he got is too loose. We have to work harder. So how can we do it? Let's take the expectation of the positive part of y. I can, for free, multiply by the indicator of the positive semi-axis of y. And then I can estimate it using any Banach space norm I want. And let's take Orlich norms. I'll estimate it by the norm of y in the original space and the dual norm. And this dual norm of the indicator is obviously connected to the probability, and we can use it to estimate the probability from below. And the faster the Orlich function L grows, the better this estimate would be. It cannot grow faster than exponential because then y plus, our y plus will not be in this Orlich space, but it can be exponential. So we choose L of exponential type. The most natural choice would be psi1, but psi1 is not going to work well here, and we consider another exponential type Orlich function. Mainly, but mainly the same as psi1. So to bound this norm of indicator from below, we have to bound the expectation of y plus below and the Orlich norm of y plus above, and the main part in it is bounding the exponential moment above. The first part is easy. We know how to do it. Since the expectation of y is 0, the expectation of y plus is just 1/2 expectation of the absolute value of y. And bounding the expectation of absolute value below is a piece of cake, where it's done, for example, in proof of the Hinchen inequality. If you know the second and the fourth moment, you can do it. And the second and the fourth moment can be calculated explicitly. The problem is what to do with the exponential moment. There is, all large deviation theory is devoted to bounding exponential moments, but here we have this plus, which messes the things up, and we want to get rid of it. So let's get rid of it, and of course, and we can estimate it with the usual moments, and this would not be a big deal. This is a triviality. The exponential of lambda y plus is pointwise less than this sum. This is a triviality, and this is not very helpful. However, we have an additional condition that the expectation of y is 0 And we can get some mileage in it, actually a lot of mileage. We can get a coefficient 1/4 in the second exponential moment. Actually, if this second exponential moment is too large, we can do even better, but we do not need it in our proof because the lambda we use doesn't satisfy this condition. But this 1/4 is going to be important. Okay, so instead of this y plus, we have a usual Laplace transform. What can be better than that? And now we have to bound the Laplace transform. So now it's time to recall what our y is, otherwise we don't have much chance to bound it. This is a quadratic form. Use our sub-Gaussian random vectors. If their coordinate were independent, we could use Hansen-Wright. Actually, with some effort, Hansen-Wright can be carried over here as well. But it turns out that it also incurs losses. And if we want to get a relatively tight estimate, we would like to do better than Hansen-Wright. And the way to improve it is to get inside the relative Laplace transform proof of Hansen-Wright inequality. And inside this proof, use the spectral structure of this quadratic form. It turns out that it can be split, and the main part will have one positive eigenvalue, the rest will be negative. And this can be used in the Laplace transform estimate, and this will lead to 1/17. So as I promised, I finished a little early, and since I'm the last speaker, let me thank the organizers for this wonderful workshop.
Yeah, thanks, Mark. Yeah, thanks for a very intriguing result. So first of all, yeah, are there any questions?
Yes.
Please go ahead.
Just a couple. Let me narrow down to a couple. So first of all, does your result implies that if you take any decreasing distribution that's supported on a cube and take IID copies, automatically you get the bound for that as well?
Not any decreasing,
Maybe
but
increasing. Maybe it should be increasing.
and even not on the cube. Actually, it can be extended to a larger class of random variables, and probably you can guess which class.
Log concave?
Exactly. This notion pops up every second line in the first proof. The only part of the proof which is which did require the exact uniform density was the Fourier transform argument, the characteristic functions argument at the very beginning of the proof. But this can be done separately, and this can be extended to log concave measures.
Of course it can. I mean,
it's not so directly, of course, but it can.
Wait, Mark, can you state the version for log concave measures?
For any, okay, let me go to the very beginning. No, it's not this. Okay. So suppose that xi's are log concaves on R, and the variance is bound, zero expectation variance bounded above, and the density is bounded below on the interval negative a. Then the density is bounded below, the density of the marginal is bounded below if the shift doesn't exceed a.
And I was wondering, Mark, also about the converse, like upper estimate, but if you from below requires that the shift is big enough. Do you see what I mean?
No. Upper estimate for big shifts is concentration.
Not necessarily big. Like suppose you know that the shift is, well, actually fix a shift. Now for this specific shift, what is the maximum density? Maximum hyperplane section. If the shift is zero, suppose you figure it out.
If it's a cube, and if it's a hyperplane section, the upper estimate was obtained by Koenig and Kaldovsky. It is tight if the shift is zero, then it coincides with ball. It's not known whether it's tight for non-zero shifts.
But they have some degrees in function.
Yes.
Any other questions?
Mark, may I ask you, Mark, can you return to this inequality about Laplace transform of the y plus? I didn't realize why it was important to get a coefficient smaller than 1.
Why? Because because these exponential moments, both of them, grow pretty fast, and we are after a relatively tight estimate.
And why does it help to have here smaller coefficient?
Okay, smaller coefficient means that smaller coefficient means that I can before it I can introduce the Orlish function L with larger lambda. And this norm will be still small.
Good. Seems reasonable.
Okay, seems there are no more questions. So yeah, thanks to all the speakers again. Thanks to the participants for sticking around, and enjoy the weekend. Thanks again.